I'm going to draw a couple pictures on the board and then analyze those pictures as we have over the last week or so. First picture is going to have object number 1 moving with a certain velocity towards object number 2, which is stationary. We'll give object number 1 a mass. We'll make it 10 kilograms. Object number 2, we'll make it 8 kilograms. Object number 1 will be moving at 5 meters per second, and object number 2 will be at rest. They're going to collide at this point, and they're going to stick together. It doesn't matter what causes them to stick together. Maybe it's glue, maybe it's Velcro, maybe it's, I don't know. It doesn't matter. They stick together. They head off as one object. We could probably make a pretty good prediction where they're going to go. If it strikes it head on, then they're going to go off to the right after the collision, right? With what velocity? Don't know, but we know that it's going to be a velocity that's less than 5 meters per second. Because when it's 10 kilograms moving at 5, and when it's 18 kilograms with the same momentum, it's going to be moving slower, right? Not that hard to kind of wrap our heads around, I don't think. Let's actually take a look at how we'd set it up here. We'd say PI is equal to PF. We'd say M1 V1I plus 0, because object number 2 is at rest, equals M times VF. M being the total mass there, 10 plus 18, 10 plus 8, total of 18, because they're both going off together after the collision takes place. We turn around and we'd solve for VF here. Right? Okay, not rocket science, right? Okay, if you understood the questions that we did today and the questions that we did before your big long break, then this question shouldn't be hard at all. Let's take a look at another one now. Let's say this time object number 1 is at rest. It's still got a mass of 10 kilograms, but this time not moving. Let's say object number 2, which is still going to be 8 kilograms, is going to be moving downwards towards a stationary object number 2. It's going to be moving downwards at 6.0 meters per second. They collide, they stick together, they head off as one object. Where do they go? Well, straight down, as long as they hit head on and not off, not a grazing collision at an angle or something. As long as they hit right on, the wreckage here is going to go straight down. We can analyze that in more or less the same way as we analyzed the last problem, PI equals PF. This time it would be 0, because object number 1 isn't moving, plus M2V2 initial equals the total mass times VF. And we turn around and we'd solve for VF there, right? I don't think that's really any harder. This time, maybe we make V2I a negative value, a -6. Maybe a little bit harder because of that, but more or less the same question as the blue one there. Okay, blue and the green, pretty much the same question. One's on the x-axis, one's on the y-axis. Only difference, really, right? What do we do, though? What do we do if we see a third question? What do we do if we see a question where object number 1 is going this way, has a mass of 10 kilograms, has a velocity of 5 meters per second to the right, just like it did in the blue problem up there. But this time object number 2 isn't at rest. Object number 2, which still has a mass of 8 kilograms, this time is moving downwards at 6 meters per second, just like it was in question number 2. So it's kind of a combination, right, of the blue question and the green question. Got object number 1 moving to the right, object number 2 coming downwards. They collide at that point right there that we're labeling with an X. They stick together, just like they did in question 1, just like they did in question 2, the blue question and the green question. Where do they go? Where does that wreckage go? It's a little bit harder this time, right? In the blue question, they went directly to the right. In the green one, they went directly downwards. Where are they going to go in the black question here? Cool. Yeah, but where? I don't need a number for the angle here, but a rough direction. Is it going to go like up and left, or up and right, or where are they going to go? Down and right. Okay. Exactly where down and right? We don't know that yet. but we can make a pretty safe prediction that they're going to go down and right. You had rightward momentum before the collision, you have to have rightward momentum after. You have downward momentum before, you have to have downward after. So combined, it's going to be down and to the right. So how do we solve this problem? How would we solve this problem mathematically? Okay, we solved the blue one, wasn't very hard. Solved the green one, wasn't very hard. How would we solve the black one? Well, here's what I want you to see in this. This black problem that we've just set up is exactly the same as the blue problem and the green problem that we've just gone through and agreed that they were pretty easy. All we're going to do in this black problem is break it up into two components, an x and a y, because you got two dimensions here. Break it up into an x and a y, two separate problems. The first problem will be identical. The x problem will be identical to what we did in blue here. Pi equals Pf. We're going to say M1 V1I plus 0 equals MVF. Can anybody explain to me why M2 V2I is 0? Even though in this problem, object number 2 is moving? Because it's only moving on the y-axis. And we're analyzing which axis? So as far as x goes, how much of that 6 meters per second is on the x-axis? None, right? None of it. So we can turn around and we can solve for VF there, for the x component. Then we do the y component. What's the y component look like? Exactly like the green problem there. Exactly. Pi equals Pf. We're going to say M1, we're going to say 0 plus M2 V2I equals MVF, the combined mass times VF. Why 0 there? Object number 1 is moving at 5 meters per second. Why do we say its momentum is 0? 2 seconds ago over here, we said it was M1 V1I. Why is it 0 now? Quinn, you got an answer for me there? Good. Good. What are we analyzing right now? The y-axis. Quinn just said this 5 meters per second is on the x-axis. In other words, none of it is on the y-axis. What I want you to do when you solve a problem involving x and y here is treat it just like the blue problem that you could have done at the beginning of the day today, easily. Treat it just like the green problem that you could have done at the beginning of class today, easily. Treat them like that. Don't make it hard. Don't look at that black diagram and say, oh, whoa, what do I do here? But do exactly the same thing. When you're doing x, pretend there's no y. Okay, when I did x up here, what did I do? Pretend there's no y, because there was no y. Do the same thing here, pretend there's no x, because there is no x. Well, here, you got to pretend there's no y, and you got to pretend there's no x. Solve for VF, x component. Solve for VF, y component. And then we're almost done. What do you think comes next? A little bit of trig, right? Physics 20 comes next. That's what comes next. Whenever you have an x component of something and a y component of something, you can combine them using some trig. Here's the x component. Here's the y component, whatever we got. The resultant velocity is the combination there. We can find VF by the Pythagorean theorem, and we can find the angle at which they go off. If somebody, I forget, it was Cole, I think, said that it was going to go down and to the right. We can predict now exactly what angle down and to the right it's going to go by just using a little bit of trigonometry, probably the tan function there, right? This should look familiar because we've done it this year. This should look familiar because we've done it this year. This should look familiar because we did it last year in Physics 20. How is this problem harder than anything we've done yet? It isn't. How is this problem longer than what we've done? Well, because it's really 3 questions in one. It's an x and a y and a vector analysis question. It's 3 times the work. It's not any harder. Just a little bit more of it, that's all. I got a little bit of stuff for you to write down, which basically just summarizes what I just said. When analyzing a collision or explosion, I should say or explosion, not of, a collision or explosion in 2 dimensions, that's with the x and the y, you're going to break it into 2 separate problems, the x and the y, just like we did right here, right? Okay, you got a blue problem, you got a green problem. Hey, you can solve those. You get the black problem here, just make it like the blue and the green problem. Break it into 2 separate problems, the x and the y, and then you're going to recombine them. When I was going through that example, you guys nailed it. You guys knew exactly why M1V1I was 0 and why M2V2I was 0 when it was. Okay. Why? Because, well, when we're analyzing the x component, we pretended there was no y. Anything that was on the y-axis was 0. When we're analyzing the y, we ignore anything on the x. And then we got to go back to physics 20. And recombine them. By using the Pythagorean theorem to find the hypotenuse and a little bit of trigonometry to find the angle. That trig, by the way, will typically be the tan function or the inverse tan function because you're going to have the opposite side and the adjacent side. You're going to use tan to find out what that angle is. Let's take a look at this one example on page 492. We got a quarterback who's 90 kilograms, which is almost twice. No, it's not twice my weight. 70 kilograms. So it's quite a bit heavier than I am. He's quite a bit heavier than I am, but not twice my mass. Moving forward moving at 7 meters per second at 270 degrees. What does that mean? I don't like that notation because they don't use it in physics 30 on diploma exams at all. I'll draw the picture for you in just a second, okay? And you'll see what the 270 means. He's tackled by a 110 kilogram linebacker running at 8 meters per second at 0 degrees. What would be the velocity of the center of mass of the combination of the 2 players immediately after impact? Center of mass is where the mass of the wreckage, for lack of a better term, can be considered to be concentrated. In other words, they go off as separate objects, but if they went off as one object, this is where they'd go. Okay, this is where the center of mass goes. Let's look at the angles here, the directions here. If you look at an x-y coordinate axis, we would consider this to be 0 degrees. This would be 90 degrees. This would be 180 degrees. This would be 270 degrees. And this would be, well, you could say it's either 360 or 0 degrees. So if you've got a quarterback going at 270, then that means the quarterback is going this way. We're going to label that as object number 1, 90 kilograms, and 7.0 meters per second. We'll finish this up tomorrow, okay? We're not going to hold you for another 5 minutes here. We'll pick this up here tomorrow right where we left off. Remember, tonight, hey, you got a lab due on Wednesday, a big lab due on Wednesday. And also worksheet number 3, not homework, but if you need something to do and you're looking for some extra practice with conservation momentum, then work on worksheet number 3. Okay, that's it for today, guys.